Royal Astronomical Society, and normally I would be teaching GCSE astronomy and I go into schools and see people face to face, but of course at the moment we aren't able to do that. So we are going to have a really fun session hopefully today, in the style of a school lesson, but obviously you're all in your homes and I'm in mine. And I quite like this because it is a little bit like planning a mission to Mars. I mean, imagine if we were traveling to Mars and we weren't allowed to go outside because we were in a spacecraft and it took 2 years. How would you feel? How would it be being confined to one space with just your family members? And this is really, really good practice if you're interested in working in the space industry. So I kind of like it, even though it's a little bit stressful at times. So the first thing that we're going to do is I'm going to talk to you about one specific topic, which you will learn when you get to kind of GCSE level. For those of you that are at GCSE level already, then there you go. And I'll talk to you about the life cycle of stars for about 40 minutes, and then we will have some time for question and answers at the end. So I'm just going to share my slides with you. There we go, and I'll just put that on. Right, okay, so hopefully you can all see that. I think you should be able to. And off we go. Right, okay, I'll just check. Yeah, okay, I think we're good. Okay, so the life cycle of stars. Well, the first thing I wanted to tell you was so a bit of my background, because I know at your age in secondary school you're kind of always thinking about careers and what subjects you might choose when you're a bit older and what you might do when you go to university. Well, I got interested in the space industry when I was about 13. I saw a film called Apollo 13, which was based on true events when a mission to the moon went wrong and the astronauts on board the spacecraft had to work out how to get back to Earth safely. And that completely inspired me into wanting to become an astronaut and wanting to work in the space industry. So I did sciencey A-levels, but I also did Spanish. And then I did physics with astrophysics at Manchester University. And then I continued my studies and I did something called a PhD. So I studied for another 4 years at the Mullard Space Science Laboratory, which is part of UCL. And at the end of that, I basically wrote a book with all my science experiments in and got tested on that book and ended up being awarded my PhD. So now I'm Dr. Sheila. So I can't save you from coronavirus, but I could tell you about space. So that's my doctorate, is all about space rather than medicine. But during my career, I've had a really, really cool time. I've got to travel all over the world. I've got to do fun science experiments on stage. I studied Saturn during my PhD. I've met some incredible people and I absolutely love my job. And now what I do is work for a place called the Royal Astronomical Society, which is a membership organisation for astronomers and geophysicists and space scientists all over the globe. We've got just over 4,000 members, and the offices, whilst currently shut, are based in London, in central London. We've got the second largest astronomy library in the country. And in the library, there are books written by Newton and Galileo and other really cool people. And we have a really nice building. So if you are ever in central London and you do want to visit when we're allowed to move around again, then do let me know and we can try and work something out. What you can see on the bottom left of the picture is a man called William Herschel, and he was the person that first found the planet Uranus, and he did lots of other cool astronomy, and he has a really amazing sister called Caroline Herschel, which I'd like to tell you about some other time. But I like to show the picture because next to him, the guy next to him, is Professor John Zarnecki, and both of these people have been presidents of the Royal Astronomical Society, but within 200 years of each other. And I think it's uncanny that they actually look quite similar. They even have the same haircut. So they're 200 years apart, but they even look like each other. And what I'd like to do going forwards for the next 200 years is change the face of astronomy. So all the lovely faces that I can see in front of me today. I'd love for you to be part of the space industry, whether you're astronomers or astronauts or anything else, just to change the face of astronomy from the lovely gentleman in the bottom left hand corner. So if you are interested in the space industry, it's not just about being an astronaut. There's lots of cool things that you can do. Obviously an astronaut would be super fun, but there aren't that many jobs as astronauts. There's been just over 500 technical astronauts in the history of mankind, of humankind, but there's lots of other jobs that you can do if you're interested in space. You could be an astrobiologist, and you could use biology to work out whether there could be life like us on other planets, and you get to travel to extreme environments like the Antarctic or the desert. You could be a radio astronomer, you could be an engineer and build parts of satellites. You could be a space weather risk manager, you could be a planetary scientist like me, you could work in the Antarctic, you could work at the bottom of the ocean trying to find out if other planets are similar to the Earth. Or there's more unusual jobs in the space industry, for example, space lawyer, space artist, space journalist, and I even saw an advert for a space vet recently, because we are taking more and more animals up into space, and we need someone who, you know, we need people that can actually look after those animals in space. So basically, if you're interested in space and you are interested in other things, you can work in the space industry. There is a job for you. You can literally do anything. There's space chefs, space people that are very good at, you know, very creative and very good at sewing, could design astronaut spacesuits. So there really is a place for you in the space industry. Okay, so today I'm going to talk to you about the life cycle of stars, and it's quite exciting because obviously we have the sun in the center of our solar system, and the sun is a star, and the life cycle of stars is a bit like the life cycle of a human being. Stars are born, stars live and they grow and they shrink, and then they do die of in a way. So the circle of life for stars is, you know, you can kind of think that that's similar to the circle of life of human beings. So we'll start with stars being born, and stars before they're born, they are called protostars, or it's kind of like a pre-star stage. And what happens is there's lots and lots of dust and gas in space, and that's generally left over from the life of a star before it. And gravity causes the dust and the gas in a stellar nebula, or a nursery of where stars are born. The gravity causes this dust and gas to collapse in and become a lot more dense, a lot more thick and heavy and concentrated. And because the density has increased, the temperature starts to increase. I'm sure you'll learn at school at some point that density and temperature and pressure are all related. So the temperature increases, and that increases as it increases until hydrogen, so the gas hydrogen and other light elements like helium, are able to start burning in a nuclear fusion process, or a sort of a pre-fusion process. And that causes the gases to start burning and give off energy. And the energy causes the middle of that protostar, the core, to become brighter and hotter, until you end up with a very baby star or a protostar. And some of these videos are a little bit grainy, but they'll give you the idea of what's going on. So we have our protostar, which is a baby star, and we are able to photograph some of those. This is not a real photograph, sorry, by the way, but we are able to photograph star forming regions, or nurseries where stars are formed, and they tend to be very gassy regions, lots and lots of gas, and then the gas comes together under gravity and then starts to burn hydrogen and helium, and the protostar is formed. So you've got this hot gas, heated because of pressure and gravity. This phase lasts about 10 million years, which sounds a long time, but as we start to learn about the life cycle of stars, you'll realize that 10 million years is not very long. And we have this sort of pre-fusion stage. So fusion does start to occur, but not enough for the protostar to become an actual star. That happens later on. Okay, so in the life cycle of the star, there are two different tracks. I've started in the stellar nebula, in this star nursery with the protostars, and then a star can take two different tracks depending on how big it is. So the first track I'm going to talk to you about is the average star life. And this is very much what our star, our sun, will do when it starts to go through its life cycle. Our star at the moment is pretty much in this sort of average star section. So it's not even halfway through its life. So we don't need to worry too much about it dying. And I will remind you of that as we go along, because some of this stuff does sound quite scary. So the sun at the moment is a main sequence star, which means it is in the sort of main section of its life. It's the part of its life that it lasts the longest. So it's probably, if it was a human, it would have been through the birth and the kind of childhood years, and now it's in its adult years, which lasts the longest in the sequence of a star's life. So main sequence stars, like I said, very much like the sun. They are hotter and brighter than before because the fusion, the energy giving process has really started. So it's in full flow. The protostar has gone from a pre-star to a main sequence star phase. And the star's much hotter and brighter because it's releasing a lot more energy, and there's radiation coming out from the core outwards. So it's actually giving off energy. And we are familiar with this because our sun is a main sequence star. It's giving off energy, it's burning hydrogen and helium. And if it wasn't doing that, basically we wouldn't be here. The radiation and the energy and the heat that's coming from the sun is what has helped us evolve on planet Earth, being just at the right distance away from the sun, that we are able to evolve and grow without being too far away that it's too cold, or too close and that it's too hot. And the interesting thing about the main sequence star is that it's the pressure out from the burning and the pressure in from the gravity, and the forces are all balanced, and we call that equilibrium or equilibrium. And that's because all the forces are balanced. So the inward forces pushing down on the star, the gravity, exactly equals the energy and the radiation forces pushing out on the star. And that's what keeps it in the main sequence for a very long time. And this process lasts for billions of years. Now, we think our sun is about 4.5 to 5 billion years old, and we think it will stay in this main sequence state for about another 4.5 billion years. So the sun and other normal average stars do burn in this state for billions of years, and then once they start to run out of fuel, then they go on to their next state. So the main sequence star is when you have the hydrogen fusion really happening, so the energy is being produced by hydrogen turning into helium, and the star is really a proper star by this stage. And this stage can last billions of years, so our sun has got to this stage, and we think it's going to last another few billion years, so we don't need to worry about anything just yet. And it's stable. It's a really stable process because the forces, the two forces, the gravity force pushing in and the pressure from the energy being created pushing out, is equal. So it's in equilibrium, and that's really important. It's quite a difficult concept to think about because we only know so much about forces at this stage, but it's really important because we want this star to be stable. We want our sun to stay the same size and the same shape and giving off the same sort of energy. If it was unstable, if it suddenly started growing or shrinking, that would be quite sort of dangerous for us. So it's really important that our sun is stable at the moment. So the inward force of gravity is balancing the outward force from the radiation pressure. But that does change. So eventually, a star like ours will start to run out of hydrogen. It has lots and lots of hydrogen in it, but you know, the hydrogen is being changed into helium, and eventually it will run out of hydrogen. And what that means is that the fusion will go down, so the energy that the star is giving off goes down, and that reduces the forces that are coming outwards, and that means gravity starts to take over. Gravity is a really small force, but it is the most important force when you're talking about space. Everything in space is basically there because of gravity, and if we didn't have gravity, the solar system wouldn't be in place, the stars wouldn't have formed, the universe wouldn't really be what it is today. So gravity is really, really important. So fusion has decreased, which means the outward force of this radiation pressure has gone down. And that means the forces are unbalanced. The star's not stable anymore. And gravity can now push down on this star and causes the star to start to collapse and start to shrink. So we had our star that was in equilibrium, but gravity now can push down on it, and the core starts to collapse. So the inside of the star starts to shrink. And what that means is that because the core collapses, and if you've got a smaller area but the same amount of stuff, the temperature can actually increase. And then that means that even though the hydrogen's gone, the helium can start causing energy and start burning. So it's kind of like a little process, one after the other after the other. So just as a recap, we have our main sequence star, a bit like our sun. There's lots of different layers. So there's the photosphere on the outside, and then the radiative and convective zones going in. And then we've got the core right in the middle. And the star is burning energy in a nuclear fusion process. But when those two forces, the pressure from the radiation and the gravity, become unstable, the core goes in, the core shrinks, the temperature increases, and then we get onto the next phase of a star's life. And that's called the red giant. So the temperature has increased, which means that the core's got smaller and the temperature's increased. And then eventually the star starts to burn off its layers. So the red giant phase is the next phase in a normal average star's life. So the hydrogen starts to run out, the core contracts because of gravity, and then the outer layers. So because the core's smaller now, it can't hold on to as much stuff. If you're smaller, you have a smaller gravitational attraction and you can't hold on to as much stuff. So the outer layers are able to kind of float off into space, and the outer layers are shed. And that means that the star actually grows. And with stars, the bigger the star, the cooler it is. And the star grows into what we call a red giant. And when the sun turns into a red giant, that's when we have to start worrying, because if the sun turns into a red giant and cools and grows big enough, it might actually envelop Mercury, Venus, Earth, and maybe even Mars as well. But like I said, that shouldn't happen for a few billion years, so we don't really need to worry too much. So at the red giant stage, you have helium and other elements which are still creating fusion, so they're still giving off energy. And it is through these processes that all the different elements that we know about are actually created. So these stars are making helium and iron and all the other elements that you have seen in the periodic table. So it's quite an important process. And once they're made and these layers are blown off into space, they can then be recycled to make other stars. So it's really, really important. And because the star has cooled down and has got bigger, it gives off more red light instead of kind of yellowy orange light. And because it's got bigger, that's why it's called a red giant. Say what you see kind of thing. Okay, so this is a massively sped up video or model of what might happen to our sun when it goes from the main sequence state into the red giant phase. So you can see here that the sun it's cooling down, it's getting bigger, and therefore Earth and the other planets, the inner planets, will be enveloped by the red giant. So there we go. There's another little video. So after the red giant phase, the core, because the core gets so much smaller, it can't hold on to the material, and the material starts to float away. It starts to spread out and disperse into space. And what we're left with is something called a planetary nebula, which is, a nebula means a ball of gas, basically. And the word planetary is left over from the 1780s, when astronomers like William Herschel saw planetary nebulas through their telescopes. And obviously their technology wasn't very advanced, and they thought they were seeing planets, but they weren't. They were seeing these big balls of gas left over from a main sequence star dying and giving off these gases. So even though they're called planetary nebulas, what they really are is a big kind of cloud of leftover and burnt out material from the end of an average star's life. So even though they've got the word planetary in them, it's got nothing to do with planets at all. It's just a big cloud of gas and dust. But they are important because these elements that are created in the stars, so like I said, hydrogen, helium, and then the other elements that you see in the periodic table, these are in this kind of gas that is being given off by this dying star, and then they go on to be recycled to be used in other stars' life. So that's really, really important, because this recycling of material also will then go into making planets. So all the planets in our solar system have chemical elements in them already. So on Earth, we can find iron and we can find helium and stuff. And that's all because of an older star in the vicinity of our star dying, giving off all this stuff, and then it being recycled to make what we have today. So it's really, really important. And then once the planetary nebula has dispersed completely, all we're left of the original star is a very, very small, dense core called a white dwarf. So the red giant eventually runs out of its fuel, and nothing else in it is able to fuse or give off energy. There's nothing else left to burn. So the star can't give off any more light or heat. And it loses its outer layers in this planetary nebula. And the core of the star is left behind. And the core is so dense and so hot that it glows white. So for stars, the hotter they are, then they're white or blue, and the cooler ones are red and orange. And because it's so small and so hot, it glows white, and that's why it's called a white dwarf. Much, much, much smaller than the stars before. So our sun will turn into, at the moment it's in its main sequence, when it starts to die, it will go red giant, it will get much bigger, and then it will give off all the gases, and then all that will be left is a white dwarf, a tiny little hot glowing core of the star that it was previously. And so white dwarfs are the leftover stuff from a low mass star. So we're talking about little stars at the moment. And they're extremely hot and very, very dense, which means like a spoonful of material from a white dwarf would be many, many elephants in terms of their mass. So very, very, very heavy. And again, these white dwarfs are stable. The pressures are, the gravity pressure that is pushing down equals the pressure that the white dwarf is giving off. So they're nice and stable. And they're so stable actually that they will live, or they will stay in that state for a very, very long time. Now, what we think will happen after a white dwarf is that eventually all the heat will dissipate, and all we'll be left with is a black dwarf. So we think that a white dwarf will eventually turn into a black dwarf, but we don't know. We've never seen a black dwarf, so this is all theory. This is people estimating or guessing what might happen. And that's because this process will take such a long time. White dwarfs will stay as white dwarfs for so many years that actually the universe isn't old enough yet for us to have gotten to a black dwarf stage, but this is what we think will happen to a white dwarf once it cools down eventually and becomes a black dwarf. But like I said, we don't actually know if that's going to happen. So stars like the sun will turn into a white dwarf and then eventually go cold and enter the stage that we call a black dwarf, but we haven't found one yet, and they're not the same as a black hole. We'll find out more about black holes very shortly. Okay, so that was the life cycle of a very average, very normal star like our sun. And heavier stars lead a very, very different and much more dramatic life. So we did the top track before, and now we're going to do the bottom track. So we start at the same place with the protostars and the stellar nebula, but now we're going to look at what happens to massive stars, much, much bigger than our sun. Now for us, our sun seems big and is obviously very important, but our sun is pretty small actually, and massive stars can be 20 times the size of our sun or more. So we go, this time now we're looking at a giant star life cycle. So we started at the same place with the protostar being born in the stellar nursery. And then there's just the reason that these stars are bigger is because they start off with more stuff. There's more hydrogen, there's more helium, and they're burning more energy, they're creating more energy. Now, giant stars have, because they're bigger, basically, they have a different life cycle. And they tend to be much bigger and they tend to have much more energy. So they tend to be different colors. They tend to be more white and blue because they're a lot hotter. They're burning more fuel and they're giving off a lot more light and heat. So they tend to be blue. So if you do look at the stars, even with the naked eye, never ever look at the sun with the naked eye, because that will, or with a telescope, unless you have proper equipment, because that can actually burn your eyeballs and you don't want that to happen. But you can, at night time, you can look at the stars even with your eyes or binoculars or telescopes. And from Earth, we can see the different colors of some of the stars. So you are able to see the different, it's very, very subtle, but you are able to see some blue stars and some yellow stars and you know, some of the different colors of the stars. So the massive stars tend to be blue because they're bigger and they're hotter. And remember, for stars, white and blue are the hotter colors and yellow and red are the cooler colors. So a massive star will live in its in this sort of average state for a bit longer because they've got more fuel. But then the main sequence phase tends to be shorter because even though they have more fuel, they tend to burn it quicker. So our sun, the phase of our sun lasts for billions of years. Massive stars would still be billions, but would be less. So they burn so hot that they would then turn into a blue giant instead of a red giant. And then eventually they would run out of fuel, very similar to the red giant phase of our sun, but because they're so massive, we call them the red supergiants. So the red giant stars are for the normal size stars, and the red supergiants are large enough and hot enough to carry on burning fuel, carry on burning all these different elements all the way up to iron. So if you've ever used iron, that element, the element of iron, is created in this red supergiant phase of a massive star. So you have your red supergiant. It lives in the main sequence and then it dies faster because it's so much bigger, but it can fuse heavier elements like iron. It has a lot more fuel, and that means when it starts to die, it does blow off into a red supergiant. It's much, much bigger and it gives off a lot more energy, and that's what we call this red supergiant phase, and that's for these high mass stars. But we still have this equilibrium of pressures. So we still have the gravity pressure pushing down, radiation pressure pushing up. But with these massive stars, the pressure is the forces aren't balanced by this stage at all, and actually gravity overtakes anything pushing outwards. so much so that everything just collapses and then it explodes. And it explodes quite dramatically in what we call a supernova explosion. And at this point, every element from iron onwards is created. So if you've ever worn silver or gold jewelry, that is created in this supernova explosion. So you are actually wearing something that was created during the explosion of a dying massive star. So that's pretty impressive, I think. I love the supernovas. I think they're quite exciting in space and quite impressive. We've never seen one physically happen like that, but we are able to take pictures of supernovas that happened a long time ago. What I'll do, I'm getting a couple of questions, but what we'll do is we will answer them at the end. So if you write them down or if you just make a note of them, I will answer them at the end. Okay, so the red supergiant collapses in on itself. The gravity is so strong that it compresses all the matter into such a small area that it causes a massive shockwave and a huge explosion called a supernova. And supernovas can, if we do see supernovas in the sky, they're very, very bright. They can last for several weeks, and it can be brighter than the light from 10 billion stars. But the actual explosion only lasts seconds, which, if you think about this life cycle of stars, is a really short amount of time. Okay, so just as a little recap, you've got your red supergiant. It's giving off the layers of elements, leaving the core behind, but then gravity starts to take over. Once iron has been created, there's no outward pushing pressure. The star, the red supergiant, starts to collapse under its own gravity. And because it starts collapsing so much, there's a massive, everything falls in until it starts to collapse into this tiny little point, and then causes this massive explosion, which is this supernova explosion. And we're still learning a lot about supernova. There's not been enough for us to really measure them, although we can see them a little bit in space, so we can work out where they are just by looking at different areas in space. And when they do happen, they're very, very quick. They only last a few seconds, but the light that is created from a supernova explosion can outshine 10 million stars in a galaxy for weeks, which is really quite cool. So you might have heard about Betelgeuse in the news not the last few weeks, but towards the end of last year. It's one of the stars in the constellation Orion, and we believe it's a very unstable red supergiant. It's about 600 light years away, so it would take about 600 years for us to get there if we were traveling at the speed of light. And it's been interesting, it's been in the news recently because it's actually dimming and brightening. So that shows that it's not stable, that these forces are causing it to get bigger and smaller and hotter and cooler. And that indicates that maybe it will go supernova in the near future. And that would be really, really cool, because people in the past have documented seeing supernova, but like 400 or 500 years ago, we haven't ever seen a supernova happen in our lifetime, and that would be a really cool thing to see. So people are keeping a close eye on Betelgeuse, which is part of the Orion constellation, to see whether it will turn into a supernova, because it would be fun to be able to watch that happening. And a long time ago, there was an astronomer called Tycho Brahe, and he was around in sort of 1600s, and he did see a supernova explosion. When we photograph it now, this is what we can see. So the matter is still being emitted and dispersed from the supernova, but he did actually document this supernova, actually the explosion. What you're looking at actually is not a visible image, it's an X-ray image. So the different colors are different strengths of X-ray. So the blue is a higher energy X-ray material coming off. but he noticed this this supernova in the sky in 1572, so a long time ago, which is quite cool. And the reason that the supernova that he saw happened wasn't actually because of a massive star dying. It was a binary star, which means there were two stars close to each other. One of the stars had died and turned into a white dwarf that we learned about before, but its energy and its gravity was still strong enough that it could pull matter from its companion star until it got so much matter it caused its own sort of mini supernova. So supernovas can happen for other reasons, not just the death of a massive star. So when we have the smaller stars, we end up with the white dwarf. When we have a kind of medium-sized star, we'll end up with something called a neutron star, which I'll tell you about in a minute. And when we have the really massive stars, so 3 times the size of the sun, we end up with a black hole. So that's what I'm going to talk to you about for the last few minutes. So the neutron star is what's left after a supernova for a sort of medium-sized star. So the material in a neutron star is kind of similar to a white dwarf. It's very, very dense. So the neutron stars might be, for example, the size of the Earth, so very small, but as heavy as the sun. So again, a teaspoon of that material is very, very heavy. And neutron stars are left behind after a supernova, so they're the core from a medium-sized star left behind after a supernova. And it's just full of neutrons. So you might have heard of protons, neutrons, and electrons. This is the reason they're called neutron stars, is because they're literally a core full of neutrons. And that means that the neutron star is very, very dense. So a small amount of a neutron star would weigh more than the Earth. Very, very dense indeed. And again, they are the pressure is equal, so that gravity won't do anything to it. The neutrons are pushing out this time, and the gravity is pushing in, and the neutron stars are very stable, and again can last like this for a very, very long time because they're so stable. Now, sometimes the neutron stars are able to turn into pulsars, and pulsars are very cool. So they're neutron stars, but they actually spin, and they spin very, very fast. And because of what they're made from, and because of the fact that they're spinning, they are actually able to create a magnetic field around the neutron star. Now, you might recognize that shape as the magnetic field of the bar magnet. So imagine a neutron star as a giant bar magnet spinning around very, very quickly. And what they're able to do then is give off jets of radio emissions. So when you listen to the radio and you hear music or you hear sound, pulsars are basically giving off sound at the top and the bottom, at the north and the south pole of the star, and they're spinning around really, really quickly. So if you imagine, well, I can't quite do it in the camera, but if you imagine that my arms are the radio sounds, the radio pulses, and if I was to spin on my spinny chair very, very quickly, every time my hand comes like this to you, you would hear a noise. And what that means is we can actually listen to pulsars in space, and they sound like a very, very fast heartbeat. I don't have a recording of one here now, but they sound like a very, very fast heartbeat. And they're quite important to us because they keep time very, very strictly, and we can use them to time different things in space. So if you, after this, if you're interested in pulsars, just Google or YouTube pulsar noises, and you can actually hear, and it sounds like a really, really fast heartbeat. And a very important lady, Jocelyn Bell Burnell, discovered pulsars when she was studying. So she was doing her PhD and she heard these noises. And originally, or initially, people weren't sure what they were. And this was quite recently, in the last 30 years, people didn't know what these noises were, and they thought, oh, maybe they are little green men. Maybe they're aliens from space sending off radio signals into space. And now we know that they're not aliens, but it's still a very cool story. So neutron stars sometimes turn into pulsars. Now, if the star originally was very, very big, then after the supernova, there's so much matter and there's so much stuff that the star won't just stop at a neutron star, but it will actually end up being a black hole. So the neutron core, the gravity is so strong that it collapses completely under gravity, and we end up with this black hole where the gravity is so strong even light can't escape, and that's why it's called a black hole, because even light can't escape. So when a star is very, very big, more than 3 times the size of the sun, even the neutron star collapses, and all we're left with is this black hole, which has such a strong gravitational field, nothing can escape at all. And for a very long time, black holes were just an idea, a mathematical idea. But over time, we've been able to collect various pieces of evidence for black holes. So we know they do exist. We can't photograph them in the traditional sense because they don't give off light, but I'll show you how we are able to photograph them in a minute. So we've got various pieces of evidence for black holes. Evidence for a black hole, number 1. What we do, so on what this is showing is different stars in the center of our galaxy, and they're all orbiting around something that you can't see. So we can tell that from measuring the orbits of these stars, we can tell that there's something that we can't see is very, very big, and it's obviously got very strong gravity if all the stars in our galaxy are orbiting around this invisible point in the center. And we believe it's a supermassive black hole at the center of our galaxy. So at the center of the Milky Way, and probably at the center of all galaxies, there is a black hole keeping everything together. So a bit like all the planets in our solar system going around our sun, all the stars in our galaxy go around a supermassive black hole at the center of our galaxy. Then we are able to see matter that is given off by black holes, but we tend to see this matter in different wavelengths, so not visible light, but in X-ray and gamma ray radiation. So if we point our telescopes in places that we think black holes exist, we are able to see the matter, so the jets of material being given off by different black holes rather than the black hole itself. And then gravity and black holes work in quite clever ways. So because the gravity is so strong around a black hole, it can actually bend light. And it bends light so much that when we take pictures of many, many galaxies, you can see these kind of arcs of light. And what you're seeing there is the light going past a black hole, not close enough that it gets sucked in, but the light going past a black hole and actually being the path of light is being bent. And that is because the gravity of this black hole is very, very strong. So they're really, really impressive, really, really impressive objects. And then more recently, there was the first ever picture of a black hole. And it was this one. You may have seen it in like on TV and in the news and stuff. And people were kind of a bit disappointed because it was a kind of a blurry blob. But this was the first time we were actually able to take a picture of a black hole, or the sort of light and matter being emitted from, not emitted, dispersed by a black hole. And it was a really, really impressive image. It was really difficult to take, and it took a lot of people and a lot of computer power to take that image. So what you're looking at is the shadow of the matter of the black hole caused by this gravitational lensing, this bending, and the capture of light by the event horizon, which shows you a bit more about what the black holes actually, how the black hole's actually structured. So this cartoon kind of shows you more what you're seeing. So the image looked a bit like these kind of fuzzy blobs. And if you imagine the black hole at the center being, and all this matter that's being emitted and dispersed, and what you're seeing is a shadow of this light, around the black hole. So it's really, really impressive. So there we go. Those are the cycle. That's the cycle of the two different tracks of the life cycle of a star. We had the average star going from an average star to a red giant, planetary nebula, white dwarf. And then we had the massive stars, red supergiant, supernova. And then if they're medium-sized, neutron stars and pulsars. And if they're massive, then they do turn into the black hole. And like I said, it's kind of similar to the life cycle of a human being. You had your protostar, and then turning from a protostar into a star. And the main sequence is kind of like infancy through to adulthood. And then the red giant or supergiant phase is a bit like your middle age. And then your white dwarf black hole is like an old age person. So the main sequence is the sort of biggest chunk of time, the adulthood of the life of a star. So the life cycle of the star, just to recap, you start with your protostars or your baby stars. They grow into stars like our sun, and they live in this main sequence for the majority of their life. And then when the hydrogen and the fuel runs out, they get bigger and cooler and turn into a red giant. And then all that material is dispersed into space, and they become a white dwarf. If they are much bigger, they will turn into a supernova explosion, and that material floats away and your neutron star is left. But if it is even bigger, then the neutron star will keep collapsing into a black hole. And it's just like a fairy tale. So once upon a time, in a nebula far, far away, a huge cloud of dust collapsed and a star was born. And it really is important, the life cycle of a star, because the main thing is that these elements that are all created, whether they're low mass or high mass stars, were created during a star life cycle. So you and everything around you really is made from stardust, which I think is quite a nice idea. So I'm going to stop sharing the slides and go back to the camera. And I have had some questions, so I will have a look at these questions now. So we'll go through the questions that people have typed, and then we can try and do the hands up version as well. So we've had a few. We don't have time to answer all of them, but I will pick some of them that are here. So there's some nice ones. Is wearing something from a supernova a bit like wearing leather from a cow? I suppose it is in a way, although we didn't sort of harm the star in order to wear the elements that are made in a supernova. And actually, like I said, everything really is made in stars, and without a star living and dying, that all that material can't be recycled into the stuff that then goes on to make our star and our planets and ultimately us. So it is a bit like that. It is a bit like that, but not quite. Could gold be in other planets? Yes, definitely. So any main sequence star, any solar system really would probably have the same sorts of elements in them, because they're all made from recycled stars, and everything in our galaxy and even our universe would be made from recycled stars, and all the stars in our galaxy and universe should go through the same processes, so there would definitely be gold on other planets. And if the star Betelgeuse were to explode, would we be able to see it during the day and the night? Yes, I believe so. I think it would be bright enough that we could see it all the time for a couple of weeks. Not bright enough that it would be harmful for us, but bright enough to see in the daytime as well. Now and again we get comets which are completely different to stars, but we do get comets orbiting the sun quite close to us, and we are able to see those in the daytime as well. So if Betelgeuse did explode, then we would certainly be able to see it in the daytime. When a star gets cold, does that mean like freezing, or for humans, is it still boiling as stars are so hot? The kind of classification of freezing and boiling is completely different on a star. So when we say a star cools down, they're still millions of degrees hot. So they're cooler than they were, but they're still very, 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 very hot. Two questions that are kind of similar. What's at the other side of a black hole, and what would happen if two black holes meet? We don't actually know. We don't know what's at the bottom of a black hole, but what we think could be possible is that a black hole is almost like a tunnel from one part of space into another. So if you imagine you had a black hole here and a black hole here and they met, they could actually cause a kind of a tunnel or a wormhole from one part of the one part of the universe to another, but we don't actually know. Let's see, what is the event horizon? So black holes are actually just a small point in space, but the event horizon is, imagine a black hole is kind of like a cone, and that's the black hole. The event horizon is kind of like the top of a funnel, where if anything gets close enough to that bit, then it ends up getting sucked down into the black hole. It's kind of like the edge of a cliff, or if you imagine a black hole being like a sink full of water, and all the water is like the light that's getting sucked down into the drain, the plug hole is a bit like the event horizon. So at the stage of a black dwarf, would it be black like charcoal or like a ball of ash? Yes, maybe. I don't know, because we've never actually kind of come across them, and we've never been able to see them. They probably would still give off a little bit of heat, but they would probably look more like coal or ash. Black, that's for black dwarfs, sorry. So black holes are black because they don't give off light at all. They suck in all the light. Have I met Tim Peake? I get a little bit annoyed at this question because I have been in the same place as Tim Peake about 100 times, and I've never actually met him. And I was supposed to meet him a few weeks ago, and then obviously that was cancelled because of all the self-isolation and stuff. So I haven't actually met Tim Peake, but I have met a few other astronauts, including Helen Sharman, who was the first British astronaut. So Tim Peake was the first British paid astronaut, and Helen Sharman was the first British person to go into space. And I know her really well, and actually she's really cool and really nice. So I don't feel too bad about not meeting Tim Peake. Did Titan once have liquid methane on its surface? So Titan is a moon. Titan is the biggest moon of Saturn, and it has rivers and lakes and rain and weather, but it's not liquid water, it is liquid methane. So on Earth, we do have methane, but methane is a gas on Earth, whereas on Titan, the liquid is, methane is a liquid, and there are rivers and lakes and streams and stuff of liquid methane on Titan. So it would be really neat if we could send a spacecraft to Titan with like a boat or something and float about in that river, in those rivers and lakes and oceans of methane, just to measure them. It'd be very cool. If iron was not created in a red supergiant star, would we still be alive? I'm not sure. I'm not very up to date on biology, but I imagine that we probably need iron. It's a pretty important thing for us to be here. So I imagine that if the situation had been even slightly different, we wouldn't be here today. And even if the Earth had been slightly closer or slightly further away from our sun, we wouldn't be here today. So everything has happened really, really specifically for us to be here now. We're really, really lucky that we're here. If we're made out of stars, why do we not explode when we die? That would be really cool. I'd absolutely love if we exploded when we died, except that would be a bit messy for our loved ones. Stars explode when they die, when they're very, very big. They explode because of the forces. And I've talked a lot about equilibrium and stability and the forces balancing. And what happens when stars die is that gravity is so strong that all the matter collapses, and then the temperatures are so extreme and the pressures are so extreme that even though everything's collapsed, they then explode in these explosions. When we die, the forces are balanced. Gravity even now is pushing down on us, but all the stuff that we're made from is pushing out to even out gravity. So we don't ever explode like that. We wouldn't explode like that when we died on the Earth. If we were in space and we took off our spacesuits, the pressure difference would be quite severe. So we aren't stable in space. And you wouldn't explode in a big mess, but what would happen is that your eyes would explode and all the air from your lungs would come out in a big rush. And if you had your mouth shut, that air would smash your teeth out. So there would be some explosions if you died in space, but not on the Earth. Okay, the very last question. Okay, yeah, so one example of spacecraft is Cassini-Huygens, which was sent to explore Saturn and Titan. We do need more of these. That's a very good point. I would absolutely love to visit Saturn again. So I used the Cassini spacecraft to do my PhD. All the data that I was using came from there. And there's so many questions about Saturn that we would love to still explore, but there's a lot of space that we would still like to explore. Sorry, there's just one last question. So I said a protostar is made of dust and gas. Where has this come from? That dust and gas that makes stars came from dead old stars. So from the planetary nebulas of smaller stars, from the supernova of bigger stars, the dust and gas floats off into space and eventually will create a new star. So it really is a cycle of life, circle of life. So I'm going to end there. It's just past 11 o'clock. The plan will be to run this session about the life cycle of stars again for the people that weren't able to join us this time. And then in a few weeks, I will do another secondary level session. If you want to suggest topics or if you want to be in touch, what I can do, I can just put, well, if you reply to the Eventbrite link that you got, then you will send an email to me. But I've also just typed my email address into the chat box. So if you want to suggest topics for the next session, or if you want to ask more questions or anything like that, do get in touch. Hopefully you enjoyed the session, and hopefully I will see you guys again in a few weeks' time. And enjoy practicing being astronauts on your way to Mars while we are stuck indoors and in our own houses. So it's really good practice to be an astronaut. Take care, stay safe and well, stay socially distanced from people, and don't get ill. Take care, guys. Nice to see you. Bye-bye.